For this constant velocity lab, I recorded myself rolling a basketball at a constant velocity in the same direction outside on a leveled sidewalk in order to justify Newton's second law, which is also known as the momentum principle. Newton's second law states that the velocity of a system changes when it is subjected to an external force from the surroundings. As shown in the formula below, the final velocity is equal to the initial velocity plus the net force divided by mass times the change in time. Oftentimes, the momentum principle can be obtained by multiplying this equation by mass to obtain the formula for momentum. Using Tracker, I found the position of the ball and corresponding time and coded this in GlowScript or VPython to get the actual points of the ball's motion so I could compare my observed results with what was supposed to actually happen based on Newton's second law. Before beginning the lab, however, I predicted that the observed motion will mirror Newton's second law and possibly result in small deviations when compared to the actual model I created. On the right is the video I recorded and uploaded to Tracker. The system in this experiment was the standard basketball, and the surroundings was the Earth and the universe. Because of this, it is worth mentioning that a force exerted on the system is Earth's gravity, but this is negligible because the object is moving along the x-axis, not the y-axis. So in this case, the net force will be equal to 0 newtons. After uploading the video to Tracker, I set the length of the basketball to be 0.24 meters based on the diameter of a standard basketball using the calibration stick, and I tracked its motion along the x-axis. As you can see, I listed the initial position, velocity, and the time interval I observed during the motion. It is also important to notice that I started the observation a couple of frames later so I could account for the ball's constant velocity and not its acceleration at the beginning. Below you can also see how I calculated the velocity from the first two position vectors and their corresponding times. After analyzing the data in Tracker, I wrote some code in GlowScript to create an actual model of the basketball's motion based on Newton's second law. To do this, I defined the initial conditions, such as the system's mass, position, and velocity to the right in the first box depicted. Afterwards, I created a calculation loop in which I updated the final velocity using Newton's second law, and then I calculated the ball's position by adding the initial position to the product of the change in time and the velocity I just calculated. This is shown here in the blue box. After iterating through each calculation, I plotted each point on a graph. Also notice that based on Newton's second law, mass is negligible because the net force is equal to 0 newtons. To see the model this creates, we can load the program here, and we realize that we get a very similar graph recorded on Tracker. Lastly, I plotted my observed results and actual model on the same graph to compare my results. As you can see, my observed data is fairly accurate and consistent with the computational model, but it does deviate from the desired results after about a second and a half. This is possibly due to the ball veering a little bit to the left in the video, which may have affected Tracker's data, but I attempted to prevent it by rolling the ball on a level sidewalk with a covering so I could also simulate constant velocity without friction changing the velocity. Overall, the ball does exhibit a constant velocity. Something to consider is that if I change the orientation of the x-axis recorded, the graph will show or display the same information, but the lines will be upward linear lines as opposed to downward depicted here to the left. And lastly, this graph supports the idea that it is not possible to determine how many pushes and pulls are added together in a lab because there are several forces and interactions not accounted for in the experiment. Thank you all for your time.